Welcome to an exploration into the fascinating realm of deep learning. Large language models are achieving incredible feats, but the underlying reasons remain largely unknown. Understanding this is a major scientific challenge and crucial for controlling future AI advancements. 2 years ago, OpenAI researchers Yuri Burda and Hari Edwards stumbled upon a peculiar phenomenon called grokking. They observed that models after initial failure could suddenly master a task after extended training almost as if a light bulb switched on. This unexpected behavior challenges our conventional understanding of how deep learning is supposed to work. This unusual behavior has sparked significant interest within the AI research community. While many have theories, there is currently no widespread agreement on the precise mechanisms behind it. This raises fundamental questions about when we can confidently say a model has stopped learning, as it might simply require more training. AI models possess the remarkable ability to generalize, meaning they can perform tasks on data they haven't encountered during training. Instead of merely memorizing patterns, they develop underlying rules that allow them to adapt to new situations. Grokking is a particularly surprising manifestation of this generalization capability. The rapid progress in deep learning over the past decade has been largely driven by trial and error. Researchers have focused more on replicating successful methods and adding their own innovations rather than fully understanding the underlying principles. This has led to a growing collection of techniques and recipes for building AI models. AI in the era of large language models seems to contradict traditional statistical principles. Statistics predicts that as models grow, their performance should initially improve but eventually decline due to overfitting. Overfitting occurs when a model memorizes the training data instead of learning generalizable patterns, leading to poor performance on new unseen data. However, large models exhibit a phenomenon called double descent, where the error rate initially decreases then increases due to overfitting, but then surprisingly decreases again as the model size continues to grow. This suggests that large models can somehow overcome the overfitting problem and achieve even better performance, a behavior known as benign overfitting that is not yet fully understood. One possible explanation for benign overfitting involves Occam's razor, which suggests that the simplest explanation is often the best. Larger models with a greater number of parameters might be more likely to discover the simplest, most generalizable pattern that fits the data effectively, finding the just so curve that avoids overfitting. Large language models are based on transformers, a type of neural network particularly adept at processing sequential data, like words in sentences. While transformers are complex, some researchers believe they share similarities with Markov chains, which predict the next item in a sequence based on previous items. However, this analogy alone cannot fully explain the capabilities of large language models. Some researchers speculate that there might be hidden mathematical patterns within language itself that large language models are able to exploit. The fact that these models can learn language by simply predicting the next word is a remarkable and potentially groundbreaking discovery, suggesting a deeper structure to language than previously understood. To unravel the mysteries of large language models, researchers are taking a step-by-step approach. They are studying smaller, more manageable models under various conditions to gain insights into the underlying mechanisms. However, it's important to note that findings from these smaller models may not always directly translate to the complexities of their larger counterparts. While we have gained better intuition, a complete understanding of why neural networks exhibit such unexpected behavior remains a distant goal. Unlocking the secrets of deep learning will require continued research and exploration, but the potential rewards are immense. In conclusion, it's possible that large models do conform to classical statistics when using different measures of complexity. While much remains unknown about the behavior of these models, as they grow, we already possess the mathematical tools to explain it. The journey to fully understanding deep learning is ongoing, and the future holds exciting possibilities.